So, good evening, everyone. I welcome you to the live session number 7 for week 7 content for the course NPTEL course Non-Conventional Energy Resources. The course instructor for this course is Professor Pratap Haridosar from IIT Madras, and I am his TA, Mr. Amit Kumar Sharma. So, like every week we are having these live session, and in this session we are covering the previous week, previous week classes content, and we are solving some sample question based on the content. So those may be helpful for you to your current assignment questions. So in today's class, we will look on to the week 7 class content. So okay, let's begin with the week 7. Okay, as of now we have covered like so much about the solar. We have covered the solar thermal power and solar PV. So in solar thermal heating, we have looked into like how the solar energy can be used to heat the water, okay, and how the solar energy can be used for cooking and various applications. And using the semiconductors, we can convert the solar energy into electricity. So we have covered all those aspects, but now we will cover these photochemical and photoelectrochemical aspects of the solar energy. So this is in this schematic you can see this is a simple schematic of an electrochemical cell. So here you can see that there are two electrodes, electrode 1, electrode number 2. Okay, there is an electrolyte. On the outside you can see the external circuit where you can see this is negative terminal and positive terminal. So positive terminal is connected to the one electrode and negative is connected to the other electrode. So out of one electrode, one will be the anode and other will be the cathode. So basically the anode is where the oxidation is happening, and the cathode where reduction is happening. So here you can see the reaction. So at this electrode, if water is present, then this water H2O converts into 4H plus protons plus 4 electron and release oxygen. Okay. So here oxidation is happening of H2. So this is anode. And this one is cathode. So these electrons are coming to this electrode from external circuit, and this H plus ion is coming through the electrolyte. And at the cathode, the reaction is this 4H plus is taking 4 electron and converting into the 2H2. So basically, from this we can see that if the water is present and some electrolyte and this combination is present, so we can generate hydrogen and oxygen. This is a basic schematic of a electrolyte cell. Okay. So now we further see that how the solar can become part of it. So in photochemical, light is directly used to enable the reactions. Okay, the reactions the previously we have seen in the previous slide. So the light can be directly used to enable the reaction, and the other part is photoelectrochemical. So in it's photoelectrochemical. So in photoelectrochemical reaction that involves the flow of current in an external circuit. So in this week we will cover the photochemical throughout our course content. So this is suppose a particle of a semiconductor material. So if this is a particle of semiconductor material, then certainly it will have some band gap values easy, as we have covered in our previous classes. So whenever the sunlight will strike on this material, okay, so sunlight is having some value h nu, and this is the band gap value at Eg. So if h nu is greater than or equal to Eg, then we know that the holes, this is the your valence band, and this is your conduction band. Okay, so holes will be created here, and electrons will be come to the conduction band. Okay, if the h nu, the energy value of the incident photon, is greater than the band gap value Eg. Okay, so this will happen. So this electron will go to the surface and take part in the reaction, that is 4H plus 4 electron, and generate 2H2. Similarly, here holes are generated, so they will again take part in the reactions. So they will react with the H2O, 2H2 plus 4H plus. These are holes, small h plus. So they will generate 4H plus ion plus O2. So this is the main reactions. If you are having sunlight, condition 1. Second condition, you should have photocatalyst. If both conditions are there, 1 and 2, so you need sunlight and both a photocatalyst material, then the water can be converted into the hydrogen and oxygen. Okay, so the 2H2O with the combination of sunlight and photocatalyst material can be converted into the hydrogen and oxygen. Okay, so as we have already seen that when the holes are generating its valence band, electrons are going to the conduction band, then there are chances of recombination also. So these electron can again come to these holes, so there can be chance of recombination also. So we have to make the material, or we have to make the properties or band gap values like this, so that there will be no recombination, and all the electron and the hole take part in the reactions, or they will directly go to the surface and take part in the reactions. Okay, so this will be our motive. So now we will see that how we can do this and how we can eliminate the recombination, because if the recombination is happening, then these electron and holes will not take part in the reactions and will not generate the hydrogen and oxygen, and they will only remain in this particle only. So here we can see the example of titanium oxide. Okay, so titanium oxide, like a material, ceramic material, semiconductor material. So we know that this is the 1.23 volt is required for this much of volt is required to break the water H2O, to break the water H2O into hydrogen and oxygen. Okay, so we need this much of potential. Now let's see. So this potential is having some, can see the values. Okay, so whatever material you are selecting for this photochemical reactions, so that material's valence band and conduction band should be like this. Like the conduction band should be above this value, and the valence band should be below this value. So here we can see that for titanium oxide, the valence band is much below this value, and the conduction band is much above this value. So this titanium oxide can be used for this reaction, and we can see that the value is 3.2 electrovolt. Okay, so here holes H plus and electrons, so the reactions can happen. So the 2H2O will react with the H4H plus and will generate 4H plus plus O2, and this 4H plus will go to the other side and react with the 4 electron and convert to the 2H2. This can be happen. The main thing is that these values. So whenever you are selecting a material, you have to check that the valence band and conduction band should be in favor of this 1.23 volt. Okay, so that this reaction can happen. Now let's see some other example also. This is CDS. Okay, so here we can see some other material also. So you can see the 1.23 volt, the required value. Okay, so with reference, this can be considered 0, and this is 1.23 volt. Okay, so this amount of voltage required. So you can see that titanium oxide is here, and zinc oxide is also here, and silicon carbide, and this CDS, cadmium sulfide. Okay, so these all four materials are, like, you can say that they are fulfilling the condition. Okay, so the conduction band is above this value, and the valence band is below this value. These all four materials can take part in the photochemical reactions. Okay, so these values are also important, like 2.25 electrovolt, 3.2, 3.2, 3.0. So these band gap values are also important, because if you are selecting a particular material, so for generating the holes and electron, the minimum energy is required. Okay, so if you are selecting titanium oxide, then you should have the photons with 3.2 electrovolt energy. Otherwise, there will be no holes and electrons. Okay, similarly for this, you need 2.25 electrovolt. So we need to select the material as per our the solar radiation also. So we will look into in our further slides that how can we optimize this. So we know that our visible spectrum wavelength is 400 nanometer violet to 700 nanometer red. Okay, and the corresponding band gap values is 3.1 electrovolt to 1.8 electrovolt. So here you can see that titanium oxide is having 3.2 electrovolt, but we know that our visible spectrum is only 3.1 up to 3.1 electrovolt. So you can directly see that this titanium oxide will not cover the visible spectrum range. Okay, will not cover the visible spectrum range. So it will not cover also the infrared range. So it will only cover the UV range only. So if suppose 100% radiation is coming, so if you're using titanium oxide, so that is effective only for the 10% of radiation, because the band gap value is 3.2 electrovolt. So we need to select the material so we can get the maximum of solar energy for our work. So these are the limitation, like only UV part of the spectrum utilized, as we have seen that because the 3.2 electrovolt for titanium oxide, so only the UV part of spectrum will be utilized. The second one is electron hole recombination. So if your like system is not quite optimized enough, then what will happen? The recombination will occur. Okay, so the electron hole recombination will occur. Reverse reaction is also easy. Reverse reaction is also easy because you are having hydrogen and oxygen, both are in same chamber. Okay, both are at the same location, so they can also again combine to generate water. So reverse reaction is also easy. So what are the approaches for this to remove this limitation? So we can do the band gap tuning. Like for band gap tuning means mean to say that we can like we can tune the band gap values. Okay, metal band gap values, so that the maximum of solar radiation can be utilized for the photochemical reactions. Okay, so we can do the band gap tuning. We can add some sacrificial agent, so that will like reduce the recombination effect, and we can reduce the particle size. So if we reduce the particle size, it will again increase the reaction rate and will decrease the recombination. And the presence of co-catalyst. If the co-catalysts are present, then the reverse reaction rate can be decreased. Okay, so these are three approaches: band gap tuning, adding sacrificial agent, and the reduced particle size, and the presence of co-catalyst. So for meaning of the band gap tuning, you can see here, this is like typo error, this is CDS. Okay. So as we have earlier covered, like PN junction, similarly we can develop a material that is having these values. One side having this CDS and other side is having titanium oxide. So it is having 2.25 electrovolt and 3.2 electrovolt. So the oxidation is happening on titanium side and the reduction is happening on the CDS side. Okay. So both are happening on different materials. Okay. So whenever the holes are generated, this will go to the this side and electron will go to the this side. Okay. So the oxidation is happening on the CDS and the reduction is happening on this titanium side. Okay. So it like PN junction only. So we can do this band gap tuning. Now you can see the EG value is 2.25 electrovolt, because if you are using only the titanium oxide, then the value is 3.2 electrovolt. So you can only use the UV radiation. But now we have reduced, we have combined some other material with this material. So the band gap value is 2.25 electrovolt also. So we can use the visible spectrum of solar radiation. We can add some sacrificial agent to the reduced recombination, like we can add the glycerol, okay, with the C3H8O3. So this will again take part, and this will reduce the reverse reaction rate, because this will generate CO2 in the reaction. Okay, it will not generate the O2, because if O2 and H2 are there, they will try to recombine. So it is generating the CO2 and 14H plus. So this H plus again react with the electrons and generate hydrogen. So here you can see that the O2 is not generating directly. So basically we are not generating the O2. Okay. Again, the smaller particle size reduces chances of encountering a defect in root surface. If we reduce the particle size, then again the reaction rate will increase and there will be lesser chance of recombination. Okay. This can be also used for the water purification, water treatment also, because suppose if here the glycerol is there and instead of this the impurities can be there, and we can decide the material so that impurity will react. Okay, and the impurity will be converted to some other like gas or like other element, and we can get the reaction or we can generate pure water also. So there are various application of this photochemical reactions, but majorly we are focusing in our work is to generate the hydrogen. So the conclusion from these slides that the photocatalysis can enable direct production of hydrogen from water. Okay. The second one is matching the band gaps of material to the voltage window needed for splitting of water. So this is very important. We have to match the band gap values. Okay. Otherwise the water splitting will not possible. Okay. So we have to decide the material having the matching band gap values with the voltage required for the water splitting. And the third one is separation of generated hydrogen and oxygen has to be enabled effectively, because both the hydrogen and oxygen are generating. So we need to separate them effectively. This is also an important task. So this was all about the solar radiation. Okay, this was all about the solar. So I think we have covered so much about the solar. We have covered the solar thermal, solar PV, and now the solar photochemical reactions also. So I think we have covered enough solar. Now let comes to the another topic. Now we will cover the wind energy. Okay. So wind energy is also a part of renewable energy. Like solar, in the solar energy, we were using the solar radiation to get the energy for our daily purpose, okay, or for our applications. Now wind is also having energy, okay, because wind is flowing with high velocity and we can use that speed to rotate some shaft, and using those shaft we can generate some power using some generators, okay. So we can use the wind power to generate the electricity. We can use the wind mechanical power for grindings, for pumping water, and for various applications. So basically, uh, Basically, wind energy is also very important part, and in today, as we are looking towards the renewable energy option, so wind energy is also having huge potential. So in historical uses of windmills means the wind farms, you can say that where multiple wind energies equipments are installed, so they are called windmills. Like, or in our earlier part, uh, we were saying we were saying these are windmills because we were using the wind velocity to grinding the grains, to grinding the pulses, okay, and all. So the historical use of windmills for the grinding grains, for pumping water, and for generating electricity. Okay, so these were the basic use for the windmills. Now, what are the requirement for the wind energy? So the first requirement is at least we require 16 kilometer per hour of wind speed. Okay, so if you want to generate the electricity, or if you want to take the power from windmills, so the wind velocity should be at least 16 kilometer per hour. Okay, and the low likelihood of bursts of wind and access to the transmission capacity. So these three requirements are there. So if these three requirements are fulfilled, then we can install a windmill and we can get the power. So this is the data from the Wikipedia. The installed wind capacity as of 2015 by the country. Okay. So the total capacity installed as of 2017 is around 550,000 megawatt. Okay. And the China is having 34%, number one. USA 18%, number two. Germany is 11%, number three. And India is 6%, number four. So as of this data, we can see that India is having a good amount of wind capacity, but we have to improve because we have to increase the renewable energy in our energy mix to decrease the dependency on the fossil fuel. So currently, we are moving toward the goal to increase the renewable energy sector in India. So other countries are having, like Spain is 5%, UK 3%, Canada 3%, France 2%, Italy 2%, Brazil 2%, and the rest of the world is 14%. Okay. So the maximum installed capacity is in China, 34%, which is, you can say that around twice the USA. Okay. So China is having like sophisticated technology and like working and spending huge capital on installing the wind farms. So this is the data for the wind power in India. Like all over the world, we are having 6% of wind energy generation capacity. Now this 6% is further divided in all over the India. And now this data is showing that which state is having how much of capacity. So here you can see that the Tamil Nadu is having 27% of capacity. Then Maharashtra 17%, Gujarat 15%, Rajasthan 15%, Karnataka 11%, MP, Madhya Pradesh 8%, Andhra Pradesh 7%. Okay, and other states like Telangana 0, like it may be 0 point something or like that. Kerala 0, others are 0%. Okay, very very small capacities. So this Mupandal wind farm near Kanyakumari is having 1500 megawatt capacity. It is the largest in India and hilly region where sea winds go through mountain passes. Okay, so these are the scenario of wind capacity installed in all over the India. As of now, we have installed 32,000 megawatt of wind capacity as of 2016. Maybe as of now, this data maybe have increased. So as of 2016, we are having 32 megawatt of wind energy. So this is the graph, like just in India, you can see that in 2006 and 2007, and like the installed capacity is quietly increasing every year. Okay, so you can see the trending pattern. So the slope is quite increasing. So every year we are trying to add the more capacity towards the wind power, and we were having target of 60 megawatt by 2022. We need to check the data. Like I think this target has been achieved. We need to look into it. So this trend is showing that our wind capacity is increasing every year. Okay. Now for the wind generation, there are two types of windmills. Okay, wind turbines. The first is horizontal axis wind turbine, and second is vertical axis wind turbine. So we'll look into these. So the first one is horizontal axis wind turbine. So these are tall towers enable accessing stronger winds. So these are tall towers, and they are enabling to accessing the stronger winds. And the blades capture wind energy throughout rotation. So they are rotating and capturing the wind energy. Okay. So the requirement for this is strong and huge towers are required. The complexity during construction, the installation is having complexity in construction and need to be turned to face the wind. So if the wind direction is changing, so the turbine should be turned, okay, so that the maximum amount of wind can be captured. Okay. So here you can see a diagram. So this is a wind turbine, like horizontal axis. So this is the axis, okay. This is the wind velocities, okay. So the turbine axis is horizontal to the wind flowing axis, okay. So that's why it's horizontal, or you can say with reference this is horizontal axis of the wind turbine. So the winds are striking on the blades and they are rotating the blades. So the blade is rotating. So this shaft is rotating. There is generator at the end. So the shaft is rotating the generators, the generator main shaft, and from there we can generate the power. We can convert the mechanical power into electrical power from this generator. And this is a large height. Okay, this is at some height, quite high height h. So this generator and these like these shafts, these blades are having some weight. So this tower structure should be sturdy and strong enough to handle and to sustain these all weights. And when the wind velocity, when the high winds are coming, so they are putting some force on the blade. So this should be strong enough to sustain those forces also. So the tower need to be sturdy and strong. Okay. So that's why we require strong and huge towers, and the complexity during construction and need to be turned to face the wind. Suppose the wind direction is like this, okay, then tower should be the direction should be like this. If suppose wind direction is like this, okay, so you need to rotate your wind turbine so that it will rotate like this and face the wind from face to face. Okay, it will generate the maximum power. The second one is vertical axis wind turbine. So in vertical axis wind turbine, it generates power independent of wind direction. So as in the horizontal axis wind turbine, the wind direction was having an important part. We have to rotate the turbine based on the wind direction. Okay, but in the vertical axis turbine, it's independent of the wind direction. So we don't need to rotate the turbine. If the direction changes, it will have no effect on the power generation. Okay. Second one is low cost. The cost for the vertical turbine is low. And third one is stronger tower not needed because the generator is on the ground. So as in the horizontal axis turbine, the generator was at the top. You can see the generator. Okay, it is at the top, so the tower should be strong enough to handle the weight of the generator and the blades and all the mechanical equipments. But in the vertical axis wind turbine, the generator is installed on the ground, so there is no need to handle the weight of the generator. So we do not require the strong tower. Okay, so the cost will be low, the complexity in the construction will be low. So these are the points, but there are some limitation also, and the limitations are low efficiency. So the vertical axis wind turbine is having low efficiency as compared to the horizontal axis wind turbine because only one blade work at a time. Okay, only one blade works at a time. The second one is may need wires to support. We need to install some wires to make it straight or make it stable, and more turbulent flow near ground. And there is more turbulent flow near ground. So you can see that this is the basic schematic of the vertical axis wind turbine. You can see the axis. Okay, so this is your axis. It's vertical, and here you can see these are the blades in different shapes. So, uh, so on this blade, if the wind is striking, so it will rotate, and this will from this side again. If this again this will come here. So at a time, only one blade is encountering the wind. Okay, so that's why the efficiency is low. The generator is at bottom, so we do not require strong tower. Okay, so these are the some advantage and limitation of the vertical axis wind turbine. So we can you can see these are the cables. We have to like tie the tower with some cables to make it straight or make it balanced. So now we have seen that two types of wind turbines: horizontal axis wind turbine and vertical axis wind turbine. Now let's look about the power generated. Okay, so suppose a larger wind turbine is having 2 to 3 megawatt capacity. So per year a 25% capacity factor. So this capacity factor means because when we design the full capacity, so it is designed based on a particular speed. But as we know, the wind speed changes every day, like every month or so. So it cannot generate the rated capacity power every time or like per day. So we can assume that if we are taking for a year data, then it will generate around 20% of the capacity data. Okay. So per year at 25% capacity factor, it will generate. So suppose it's having 2 megawatt capacity. So 2 into 10 to the power 6, okay, watt. And the 25% capacity to 0.25. Okay. Uh, on one day we are having, so in 1 year, 365 days. Okay, one day, 24 hours, and 1 hour, 3600 minutes, seconds. Okay, these are the days, these are the hours, these are the seconds. Total energy we are having is this much amount. So 1.6 into 10 to the power 13 joule. So if a 2 megawatt capacity wind turbine works at 25% capacity factor for a year, then we are having 1.6 into 10 to the power 13 joule of energy. But as we know that we require 500 exajoules, our average requirement of the world is 500 exajoules energy. 1 exa is equals to 10 to the power 18 as of our first week lectures. Okay, so we can write 5 into 10 to the power 18 divided by 1.6 into 10 to the power 13. So it's so the data comes to 31 into 10 to the power 6. Okay, so we need 31 million wind turbines. So if the one wind turbine, suppose if one wind turbine generates 2 megawatt of electricity, and when it is working at 25% capacity factor, okay, we require 31 million wind turbine to get the 500 exajoules, our annual power consumption. So this data is very huge, okay, as compared to the solar energy, because like solar, like in 1 hour we get the 500 exajoule energy, okay, and in wind we require 31 million wind turbine. So let's see further the space requirement, because if we want to install 31 million wind turbines, we also need space, because whenever we are installing a wind turbine, we have also look about the terrain, and we have to check the space, because the wind turbine should have full access, the interpret access of the wind velocity in that area. So we cannot like make we cannot develop high-rise buildings near the wind turbine. There should be totally open space for a particular area. Okay, up to particular area. Okay, so let's see what is the wind turbine space requirement. So the rule of thumb is that the 7 times diameter of windmill. So at least we require 7 times the diameter of windmill space, approximately 500 meters from the other turbines. So if there are multiple turbines are installed, so there should be 500-meter distance between the turbines. Okay. So this is one requirement. So 7 times the diameter of windmill, or around 500 meters from other turbines. Each 2 megawatt turbine needs approximately 0.5 square kilometer. So if you are installing a 2 megawatt turbine, you require 0.5 square kilometer of area. Install this wind turbine. So therefore 15.5 million square kilometer needed to power the world. So if you are planning to power the world using only the wind energy, then we require 31 million wind turbine, and for these wind turbine we need 15.5 million square kilometer to install. So roughly it's about 1.5 times the size of China or USA. It's very huge. It's not possible actually. You require 1.5 times the size of China or USA. Okay. So the conclusion is that the considerable interest is tapping wind energy both internationally as well as in India. As in our previous slides, we have seen that India is ranking 4th in the wind energy capacity. Okay, so considerable interest is tapping wind energy both internationally and as well as in India. And the geographical locations play an important role in planning windmill installation, because the average wind velocity is a major factor, and location. Okay, the various design of windmills considered historically. So various designs are available, and the various purposes are also there. So we can install different wind turbines based on the location, based on the available resources and all. Okay. Now this is the basic energy calculation for the wind turbine. So the basic formula for the kinetic energy, we all know that half mv square is the basic formula for a kinetic energy, where m is the mass and the v is the velocity. So for mass of the air, we can say the rho v, rho density, v volume, okay, rho v square, and we know the volume means the area, the wind turbine area, and suppose this is the radius, this is the, like these are 3 blades, okay, so they are having some radius, so this is the area they are covering, and suppose there is a small thickness, like small part of area, for that is considered for the generation, so that is L. So the mass will be rho v, rho al v square, okay, so the power will be differentiate with respect to time, so d by dt is equals to half rho a dl by dt v square. You can say half rho a v cube. Okay, again this will convert to the velocity. So you can see that power is proportional to velocity cube. Okay, because density will be constant. Area, suppose if you have installed a wind turbine, then the radius, what will be the area? Pi r square, because it's a circular. Okay, you are having some radius of uh, the blades. Okay, so pi r square. So the velocity, so the power is directly depending on the cube of velocity. So this, so the graph for the power and wind speed will be like this. Power is proportional to the V cube. Okay, so you can see the pattern. Okay, so as the wind speed is increasing, the power is increasing. Okay, in cubic manner. There are some performance characteristics also for wind turbines. The first is the tip speed ratio. Okay, so the ratio of rotational speed of blade to wind speed. So the tip speed ratio is the ratio of rotational speed of the blade to the wind speed. Okay, the maximum of 10 for lift type blades. So it can be maximum 10 for lift type blades. There are two types of blades, lift or drag. We will look into it. So if your blades are lift type blades, then this ratio can be maximum of 10. The second one is cut-in speed. So minimum wind speed at which the blades will turn. So the cut-in speed, like what is the minimum speed that is required? It can be in the range of 10 km per hour to 16 km per hour. Third one is rated speed. So the wind speed at which the windmill generates its rated power. So usually it levels off in power beyond the speed. Okay, around 40 kilometers. So this is the maximum power. Suppose if you're designing a wind turbine, so there will be rated power. So the maximum power that can be generated from that particular turbine. So beyond this power, you cannot generate more power. It's around 40 km per hour wind speed. Okay, the cutout speed is usually at wind speeds above 70 km per hour. The windmill is stopped to prevent damage. If the wind velocity is very high, then that can damage the wind turbine. So the around 70 km per hour is the cutout speed. If the wind velocity crosses this speed, then the wind turbine will stop working to prevent any damage to the turbine. So these are four important parameter, performance parameter. One is tip speed ratio, cut-in speed, rated speed, and cutout speed. Now there is theoretical limit, okay, on how much of energy we can tap off from the wind. Okay, so there is a Bell's law given by in 1920 based on two assumptions. The first is wind fully stopped by windmill, and second, wind unaffected by windmill. Okay, so in this one, we are getting the complete power from the wind, like wind fully stopped by windmill. If any wind is crossing the windmill, so windmill is completely getting the all power of the wind, and after that, wind is having zero velocity. And the second one is wind unaffected by the windmill, so there is no power from the windmill. So based on the calculation and all the formulas data, so we came to a fraction 16 by 27. It's very important fraction. It's called Betz's limit. So it's come to 0.59. So practically we can get only 59% of wind energy. Okay. Suppose if wind is having complete 100% energy, so the maximum theoretical limit is only 59%. So we can get only 59% of wind energy. Okay, we can capture only 59% of wind energy. But practically, when we are working, so we get only 10 to 30% of energy. Okay, so maybe the efficiency of the wind turbines around like 40% or 60%, 50%. So the final efficiency will be 0.40 into 0.59, because 59 is a theoretical limit This one is practical limit. Okay. The practical efficiency is obtained around 10 to 30% of energy originally available in the wind. So this is the graph shown for a cross-sectional area corresponding to a radius of 60-meter wind turbine. Okay. So as you can see that after 10 km per hour, wind turbine started capturing the wind energy. Okay. As the speed is increasing, the wind power is increasing. You can see it's increasing. After 40, it's maximum rated capacity. So after this, you can see the power is almost constant. It's not increasing at 70. So cutout speed, the wind turbine stopped working and power suddenly drops to 0. Okay. So this is theoretically possible, but practically we are getting it's around only this graph. Okay. So this is a difference between theoretical and practical limits. So there are two types of blades. One is drag type and lift type. Okay. So the drag type blade is having greater torque, low rotational speed, and better suited for mechanical work. So in our earlier times, we were using drag types blade where we were using the windmills for grindings, grain grindings, okay, water pumping. So we require more torque and low rotational speed. Okay. So the drag type we're using there, but the efficiency is quite low as compared to lift type. So lift type is having high rotational speed, better suited for power generation. If you want to generate electricity, then we are going for lift type. So these are lift type as having like aerofoil design. Okay. So these are higher rotation speed and better suited for power generation. So the conclusion from these slides are the power available in the wind is proportional to the third power of wind velocity. So P proportional to V cube. So power is proportional to cube of velocity. If the wind velocity is increasing, then power increasing by the cube of that increment. Okay. So small increment in wind velocity can be result of large increment in power. So wind velocity play a very important role in this. There are practical aspects that limits the range of wind velocities that can effectively tap. So that we have seen the theoretical beds limit and practical limits. So up to that limits only we can tap off the wind power. There is theoretical limits to the extent to which energy available in the wind can be captured. So practical limits will be due to the generator, due to the mechanical efficiencies, due to the due to the blade designs, due to the other various factors, and theoretical limit. Okay, that is bed's limit. Okay, so we can generate maximum 59% theoretically. We can capture wind power, and with practical aspects, we can capture slightly low. So I think we have covered about the photochemical, solar, and the wind power, basics of wind power. So based on this, we can solve some questions, some some basic assignments question. So I will give you 2 minutes to solve this question. So try to solve this question and take 2 minutes to solve and tell me the answer, and let's discuss these questions. Okay. So the first question is, in a photoelectrochemical reaction of water, titanium oxide, photocatalyst space and space gas are generated at anode and cathode respectively. So basically, we have covered the photoelectrochemical reactions, okay, of titanium oxide using titanium oxide as a photocatalyst. So there were two gases were generating, hydrogen and oxygen. So at which electrode they were generating? Okay. So take 2 minutes and try to answer. Is my slides visible to you? Anyone? Anyone online?
Yes, visible.
Okay, thank you. Try to remember that at anode oxidation is happening, at cathode reduction is happening. So based on that, I think you can recall.
Sir, first option O2 and H2.
So O2 and H2 gases are generated at anode and cathode respectively. So you mean to say the oxygen is generating at anode side. So if the oxygen is generating, then what is happening at anode? What is happening at anode? Oxidation or reduction?
It is oxidation.
Yeah, oxidation of which?
Oxidation of uh, water, no? Water molecule. No?
Yeah, water molecule. Yeah, correct. So the correct answer is O2 and H2. Okay. So the oxidation of water is happening at the anode side, and the O2 and H plus ions are generating, and the H plus ion are transferring to the cathode side through the electrolyte, and at there hydrogen is generating. The question number 2. You have to match the following steps to reach the final photoelectrochemical reactions of H2 gas generation. So there are 4 steps, 1, 2, 3, 4, and they are similar process. So you have to tell the correct statement, the correct combinations. So try to recall and take 2 minutes to solve this. What is the first step?
Incoming photoradiation.
Yeah, first of all, we need incoming photoradiation. After that, all steps are happening. So the step 1 will be incoming photoradiation. So A will combine with the third. And what will be second step when we are having the incoming photoradiation? Then what will happen?
Electron hole pair generation. Next
So
step.
yeah. Second step is electron hole pair generation, because if we are having the energy equivalent or more than the band gap value, then there will be electron and hole pair generation. Okay. And what will be third step?
Then migration of each pair to the respective surfaces.
Yeah, correct. So when the electron hole pairs are generated, so they will go from the valence band to conduction band. And then fourth step,
Recombination of electron hole pairs.
No, actually recombination we try to avoid. We want reactions, okay? So recombination is happening sometimes, but majorly the reaction occurs, okay? If we are having these photoelectrochemical reactions to happen, then reaction should be occur. So we have to avoid the recombination. So recombination is like, you can say, the side effect. We don't want it. We want to reaction occur. So the 4 steps will be: the first will be incoming photoradiation, the second will be electron hole pair generation, the third will be migration of electron hole pair towards the surfaces, and when they are at the surfaces, they will react, okay? So the reaction will occur. So the correct answer will be A3, B2, C1, and D5. Okay. Any doubt?
Oh. No, okay.
Okay. So question number 3 is, are you able to see the question?
No, right now, no.
Are you not able to see the question number 3?
No, up to second question not visible. No, it's not. So, yeah, true, false. Yeah.
It's visible here.
Visible.
Is it visible now? Na? Yeah. Okay. So question number 3 is, use of a co-catalyst in the process of hydrogen and oxygen gas generation helps in increasing rate of electron hole recombination. So take 2 minutes and try to recall the slides data and try to answer.
Sir, co-catalyst means nickel and bromide and all.
A co-catalyst, it's actually depend actually what is your like semiconductor material. So it may be it based on that actually. It can
Silicon
be
is
nickel
also
or
used.
yeah, these can be used, but you need to look into the matching actually. Matching co-catalyst you have to use. So for more detail, you can refer some textbook. But basically, the question is, what is the like, what is the work of this co-catalyst? Is it increasing the electron hole recombination or it is decreasing? Is it true or false? What is the main role of co-catalyst? Why we are using this co-catalyst?
Reduces whole pair recombination.
To
Reduces.
decrease the recombination.
Yeah, correct. Because as we know that we want to more and more reactions to happen, then we have to decrease the electron hole recombination. Okay, so we use some co-catalyst. So that co-catalyst will help the increasing the reaction rate and decrease the electron hole recombination. So the true option, so the option will be false because it's not increasing, it's decreasing. So the option will be, it will be false. Okay, so the accepted answer is false. Now question number 4 is, sacrificial agent is added to increase the electron hole pair recombination reaction. So similar like previous question, like we are also using sacrificial agents, and are they used to increase the hole pair electron hole pair recombination and for or like other purposes? So is it true or false? Try to answer this. Take 2 minutes.
It also reduces recombination, but for other purpose.
Yeah. And what is, I have also told you some other purpose also for sacrificial agent. What is that? Like we have discussed the glycerol, okay?
Some bending word you are using, bending, bending. Bending name. You are
No,
using
not
term. I am
bending.
not bending is not term. basically reduces the band gap uh, with the two types of. The actual term I'm not remembering, but
Let
purpose
me
is to.
open that particular slide for you. So I think you will be able to recall. Yeah. So here we were adding glycerol, C3H8O3.
Yeah.
So this was to reduce the recombination, and also it was generating CO2 instead of the O2. So the reverse reaction was also not happening. Okay. So here, instead of the glycerol, we can also use these methods to clean the water treatment also. Okay. So that is the important part of this. So that impurity can be reacted and can be generated in some other component. Okay. So instead of the glycerol, that impurity can take part in this reaction, and we can treat the water. So the
Small
sacrificial.
particle size. What does mean smaller particle size reduces chances are encountering defects?
So if
Which
the
smaller particles?
it means to yeah. Suppose this is a particle. So if the particle is small, then the electron and holes are directly go to surface easily. They don't want to travel more actually. Okay. So it's depend on the structure of the material. The smaller the particle size, it will be easier for the electron and hole to go to the surface, and they will take part in the reaction. Otherwise, they have to travel more, then there will be more chances of the recombination. Okay.
Okay. Okay, right.
Yeah. Let's come to the questions. Yeah. So the sacrificial agent is added to increase electron hole pair recombination reaction. True or false? So it is false. It is added to decrease the electron hole pair recombination, not to increase. It is added to decrease. So the correct answer is false. So the question number 5 is particle size reduction, space, the chances of space. Take 2 minutes and try to answer. Just recently we have discussed this again.
It decreases no electron pair combination, recombination.
Yeah, decreases. Yeah. So the correct option will be it will decrease the particle size reduction, decrease the chances of encountering a defect in root surface. Okay. So if there is no
Yes.
defect in root surface, then there will be more, the reaction rate will increase. Okay.
Yeah.
And the electron combination will reduce. So the correct option will be decrease and encountering a defect in root surface. So it will be option C. Question number 6. Match the advantages and disadvantages of different type of windmills. So we have discussed two type of windmills, vertical and horizontal axis. So every type is having their advantage and limitations. So try to link those, try to recall, and take 2 minutes to answer.
Sir, is it option second?
Second means A3. So
Vertical.
vertical axis, yeah, require more turbulent flow of air near the ground. Okay. So just rethink.
I went like horizontal axis will be complexity with respect to setting up because the equipment is huge. And
Okay.
if at all it is offshore, then it is very complicated.
Okay.
And it is easy to access stronger winds in horizontal axis.
Yeah.
B will go for 1 and for the remaining will go for A. This is how I thought.
Yeah. Correct. So the correct answer is A3, B1. So vertical axis will more turbulent flow of air near the ground. Okay. And for horizontal axis, easy to access stronger winds. Okay. And then again A2, wind energy is not captured throughout the rotation in horizontal axis. The complexity with respect to setting up, because for we require for horizontal axis we require stronger what? Why the complexity is there? When we are installing the horizontal axis turbine, why the complexity is there? What is the reason of complexity?
A lot of tying is required, no? Support is
Lot of?
required. Tie line is tie wire, guy wire is required.
No, I think you are confusing with the vertical and horizontal axis.
For horizontal, the equipments are used generally.
Okay. Now, what is the major complexity? What is the major difference between the vertical and horizontal? Try to think. In one, the generator is at the top, and in one, the generator is there at the bottom. So which one is having generator at the top?
The horizontal axis.
Yeah. So the horizontal is having generator at the top, and vertical is having generator at the bottom. So if you are installing generator at the top of your wind turbine, then it means that generator is having huge weight. Okay. So you need stronger tower. You need to, and the height is very high. So at that height, the wind velocity is also very high. So to support that weight, to support the drag force of that high wind velocity, you need very much stronger tower. That's why the complexity is there. On the other side, with the vertical axis wind turbine, the generator is at the bottom. So there is less complexity. Okay, so this is the major difference
One thing,
regarding the complexity. Yeah.
turbulence is more causing a hard problem, or high wind velocity is causing more problem? Turbulence in a vertical turbine, vertical axis turbine, turbulence is more because it is near to the ground. So
Yeah. Only and in vertical only.
my question is whether turbulent air is more problematic or wind with higher velocity is more problematic. My basic question is that.
No, it because both are different structure, na. Actually, it's depend because if you can compare only with the same, like if you are like comparing both the turbulent and velocity with vertical, then you can compare. But both are having different structures. So turbulent
Suppose
is having.
we are
Yeah.
in flight, we are going in flight when turbulence come, then
Yeah.
sudden jerk starts, plane starts moving up and down. Although
Okay.
maybe some velocity, but that was my thinking. Turbulence may be more problematic than a wind speed with constant velocity. It's not like that.
No.
But in the plane, the blades are flat, no?
Yeah. In the vertical axis, na, we are having single blades only, and the blades are structure of blades are like flat only. And in the horizontal axis, we are having aerofoil structures. Okay, aerodynamic structures of blades.
Plane is also having aeroplane. Plane and blades are plane and horizontal axis turbine are similar type. Both are having same basic principle. Aeroflight design, both.
Okay.
That way, a drag is coming, a lift is coming. No? That is the basic reason. Plane also works on lift principle. Horizontal axis wind turbines also works on lift principle. Basically,
Okay, that's right. So I think we have to look into more about the turbulent part. But the major point is that the complexity is due to when we are installing na. Then the major part is due to the like handling that weight part. That weight to measure the strength of the tower. That is the major complexity actually.
yeah, that may be the reason. Center of gravity of equipment and all the things.
Yeah, that
Yeah.
is the major complexity, but the turbulent part we have to see it more actually.
Okay. Okay. Right. Please go ahead.
So the correct answer will be A3, B1, A2, and B4. So the next question is question number 7. A large wind turbine of 2 to 3 megawatt with 35% capacity factor is installed in a region. Then the number of wind turbines required for fulfilling the energy consumption of 500 exajoules will be. Yeah, it's just a numerical. Take 4 to 5 minutes to solve this. We have already do a sample calculation in our previous slides. If you want some hints, I will open that slide. Just try to first in 2 minutes try to solve. And if you are having some problem, then let me know. I will open that slide. So from that you can take the reference. Try to find the answer. Take 4 to 5 minutes. Just simple calculation. You are having the capacity of 2 to 3 megawatt. There is capacity factors also mentioned. And the 500 exajoules is the per year energy requirement. Okay. So try to calculate the available energy from the wind and the consumption. Based on that, you can find out the number of wind turbines. First, calculate the how much energy can be generated from a wind turbine, a single wind turbine. And you know the total energy required. So by dividing that, you can find the number of wind turbines required. one hint is for you that more than one option can be correct. Okay, so as you have given 2 or 3 megawatt, so try to calculate with first 2 megawatt and then again calculate with 3 megawatt because there is no single data mentioned. So 2 or 3 megawatt, so maybe 2 or maybe 3. So try to calculate for both and try to check if the both answers are there or not. Because it's not mentioned that only one option is correct. Maybe 1 or 2 options can be correct.
I have not calculated, but I'm making a guess. In your example, you have calculated 31 million with 2 megawatt almost 2.3 like that, and with
Okay.
when megawatt is more, then it will come down little bit. It will come in 22 million. So it should be 31 and 22. This is my guess, not calculation.
Yeah, just try to calculate na basic simple just multiplication only, multiplication and division. Because the capacity changed actually. In that example, the capacity was 25% only. So here you can see 35% capacity. So
Yeah,
your one guess is correct, like 22 may be correct, but 31 cannot be, no? Because 31 was for 25% capacity. When you are increasing the capacity factor, then the number of wind turbine will be decreased because you will able to generate more power.
yeah,
So you
yeah.
will require less turbines. So 31
Yes,
will be not an answer. It's sure. So it can be 22, 15, and 10.
yes, correct. You have to calculate.
Yeah, the simple just calculation. Just think, you know the 500 exajoules. So exa, you know the unit 500 into 10 raised to power 18 joules, and you have given the wind turbine. One wind turbine is having 2 megawatt. So convert the megawatt into joules. You know the capacity, 35%. Just basic calculation. Just try to multiply in calculator. It's very simple. Just take 2 more minutes. First calculate for 2 and then for 3. Let me open that slide for your help. Yeah, this is how the power is generated. So if the wind turbine is 2 to 3 megawatt, capacity 25%, then first find out the power. First find out the energy, not power, energy from that wind turbine, from wind turbine. Per year, so we are considering 365 days. Based on that, you can find out the power. You can find out the energy, and the the 500 exajoules will be required. How much wind turbines? Just divide the 500 into 10 power 18 by the energy of one wind turbine. You will get the number of wind turbines required. This is a good hint. You can do the calculation based on this. Just change the capacity factor only, because we have given in our question 35% factor. So maybe in your assignment or exam, it can be any factor, 30%, 40%. Try to know the concept, so we'll calculate easily. Anyone answer?
22 and 15.
Yeah, correct. Very good. So the correct answer is 22 and 15. So this is the basic formula. Okay, first find out the power generated from one wind turbine. Okay, so we can like do the basic calculations. We are having 2 to 3 megawatt. So just consider first 2 megawatt. So 2 megawatt. So the power we have given 2 megawatts. So to find out the energy that will be available from this wind turbine throughout the year with 35% capacity. So multiply 2 into 10 to the power 6 into this 0.35 capacity factor into, now this is in watts. Okay, so joule per second. So convert in only joules. So multiply with the number of seconds available per year. So 3600 into 24 into 365. Okay, how much is coming? Will come into 0.35 into 3600 into, so this will come around 2.2 into 2.2 into 10 to the power 13 joules. Okay, so you know the 500 exajoules will be required. So just divide by this 500 into 10 to the power 18 divided by 2.2 into 10 to the power 13. So you will get around, it will be around 22 into 10 to the power 6. The exact will be 2264981. So roughly you can say 22 into 10 to the power 6. Okay, you require 22 million turbines if you are having 2 megawatt of wind turbine with 35% capacity factor. Okay, similarly, if the capacity, if the wind turbine power is 3, okay, so just replace this 2 with 3 and do the same calculation. So you will get the answer like 15. Okay, so the correct answers will be 22 and 15. Anyone, any doubt? Is it clear?
No.
Is it clear?
Yeah,
Okay,
clear.
Okay. So the correct answer will be 22 and 15. So next question. So what will be the total approximate space requirement to install all the wind turbines calculated in question number 7? So you have calculated like number of turbines as per question 7 data. So you require 22 millions or 15 millions wind turbines. Now calculate the space requirement. In one of our slides, we have seen the like basic space requirement for one turbine. Okay, so based on that, try to find out the answer for the same. And just another take 5 minutes to solve this. Let me know if you need any hint. Try to recall the data, because every wind turbine, whenever we are installing wind turbines, we require some minimum spacing between the wind turbines. Okay, because we cannot install wind turbine adjacent to each other, because they will block the wind velocity and the efficiency will be very, very low. So there should be a certain distance for a single wind turbine. So based on that, we need to find out the space requirement. So you can take the data from question number 7. The data is you require 22 million wind turbine and 15 million wind turbine. So if you want to install 22 million wind turbine, then what is the space requirement? And if you want to install 15 million wind turbine, then what is the space requirement? Find the both answer and just compare the answer with the options for question number 8, and check which one is the correct answer. Let me help you with the slides that we have covered for the space requirement. So this was the slides that we have covered. So there are some basic rule of thumb and approximately the distance that is required. Okay. So the first rule of thumb is 7 times the diameter of windmill. We have not given the diameter, so we can not apply this thumb rule. And we have given that each 2 megawatt turbine needs approximately 0.5 square kilometer. So suppose if you are having a 2 megawatt turbine, so approximately you will need 0.5 square kilometer of area for that one single wind turbine. I think this data can be useful for you to calculate the space requirement for 22 million and 15 million wind turbine. Because if you want to fulfill the annual energy requirement of the world, then you require, as you have calculated, 22 and 15 million wind turbine. Now you have to find out the space required for these turbines to install. Then what will be the answer?
Sir, one may be 11 million square kilometers.
Yeah, because if we want to install 22 million wind turbine, and we know that one wind turbine require around 0.5 square kilometer of area. Okay, so for 22 million wind turbine, we require around, just multiply with it, 22 into 0.5, it will come around 11 square kilometer. Now if we are having 15 million wind turbine, then again 15 into 0.5, it will be around 7.5, but 7.5 is not an option, only 11 square kilometer is in option. So the correct answer will be option C, 11 million square kilometer. Any doubt?
No,
No,
clear.
sir.
I was
Okay.
I was adding 7.5 and and 11. That's why
Okay.
I was not, because question was like total area. So total means for considering those 15 and 22. So that's why I was little bit confused.
Okay.
Right.
Total means like if you want to install complete 15 million, because either your plant will be having 2 megawatt or okay. So if you are using the 2 megawatt, then what is the total area? Total means that we have to install like 22 million wind turbines, na? Then like each wind turbines required 0.5 square kilometer. Then total the sum of the all areas required for the wind turbines.
Either well, from one option we had to take, na? Either 2 with 2 or either with 3.
Yeah. Suppose if in options there is 7.5 is also mentioned, then you have to tick that, because in question number 7, na, you can see we have given 2 or 3. Then the correct answer 22 and 15, because we can either consider 2 or we can consider 3. Okay, so we have calculated from both. So we have come up with the options B and option C. Now for space requirement also you have to take both options. Now check the options. When you check the options, then only one option is there. So there are two answers, 15 and 7.5. But only 15 is there. Sorry, 11 and 7.5. So only 11 is there. That's why only option C is correct. If suppose instead of 6 there is 7.5, then 11 and 7.5 are correct.
Right.
Okay. So always whenever you are solving questions in assignments or in your exam, when it is not mentioned that only one option is correct, then try to check all the options, because more than one options can be correct. Okay. Just don't mark down the first options you get. Na? Try to check all the options, because some questions are slightly tricky. Okay, so try to check all the options, because so you will get full marks. Otherwise, you will get partial marks. Okay. So this question number 9. Name the points A, B, C, and D in the below given ranges. So we have discussed this diagram based on the points and process. Take 5 minutes to process this diagram and try to answer.
Sir, option C. A is no power generated. B is power available in windmill. C will be when it reaches the rated power, and D will be shut down.
Okay. Can you also explain the reasons why the C and why the D and the approximate watt speeds these are happening? Can you recall those data? Like suppose A, you are saying that A is no power generation. So we are having some particular speed limit. After that, only power is generated. So can you recall that data? Because that data can be also a question in your classes or exam. So try to recall this data also. What is the data for A limit? Your answer is correct. Now, what is the data? Just tell me the data.
Less than 10 kilometer per hour wind speed is.
Yeah, 10 to 16. Yeah. So if the speed is less than 10, then there will be no power generated. Okay. And then what about the B?
it is cutting more than
So as
16.
the, as the speed will increase, so the power will increase up to a particular limit. So that limit will be the rated power limit. Okay, so that will be around, maybe depend on the wind turbine to wind turbine. Just as we have discussed in our this slide, so we have taken a particular value 40 kilometer per hour. Okay, so the C value will be 40 kilometer per hour. Then what about D? At what wind speed the wind turbine will stop?
70.
Yeah, correct.
Cut off.
Yeah, cut off. So if your wind turbine is having speed more than 70, then it can damage the wind turbine. Okay, it can
Yes.
it can damage the generator also, because maybe the generator shaft is not handle that much of RPM. Because if the wind turbine, if the wind speed is high, it means the RPM will be high. Okay, and maybe the generator cannot handle that RPM and torque that are available from that wind speed. Okay, so maybe the shaft will break, the generator will break. Okay, that's why for a safety purpose we have some limit. After that limit, the wind turbine will stop working. So the correct answer will be option A will match with the 3, B will match with the 2, and the C will match with the 4, and D will match with the 1. So the correct answer is it's, I think, C. This one. This is the correct answer. Let's come to the question number 10. So wind energy is calculated using Bernoulli's equations. I think we have not covered in our slides. I think in today's slides, maybe Professor has covered. So let's try to answer. Basic, just what is the Bernoulli equations? You can then just that will be the right answer, I think.
Half rho v square plus rho h plus p is constant.
Rho v square, you mean to say the option number C?
Yes, rho v square plus rho h plus p is constant.
Okay. Just try to think, because I think your answer is partial correct, I think, because just try to think.
Fourth one, half rho v square plus rho gh plus p is constant.
Yeah, because we also need the G in. Okay, so the Bernoulli equation is half rho v square rho gh plus p is equals to constant. So this is the basic equation, and from this derivation, further calculation, we can calculate the wind energy, or like we can I think also calculate the bed's limit. Okay, that's 16 by 27. So these all are derived from these equations. Maybe some other equations are also maybe part of that calculation, but this is for certain. So half rho v square plus rho gh plus rho is will be plus p equal to constant is correct answer. Now let's come to mini quiz for true and false. Now there are 5 questions. Try to take 5 minutes, 5 to 10 minutes. Try to answer. The first one is, during photocatalysis, to split water, hydrogen, and oxygen form in the same chamber. Is it true or false? If is it true, then why? If is it false, then why? Try to think about for 2 minutes. In our initial slides, we have covered it.
First one is true, na? In the same chamber. There's no any partition. Same chamber.
Yeah, correct. They are in the same chamber because there is no partition, and thus we are having the particle and the water and the solar light. Okay, so the split of the water will split, and we will get the hydrogen and oxygen. So the first one is true.
True.
Now the question number second. Harnessing wind energy is an indirect way of harnessing solar energy. Is it true or
Also
false?
true. Because
True.
correct, wind also produces due to solar effect only.
Yeah, correct.
True.
Because due to the temperature difference only, we are getting the
Wind.
winds. Okay, so the harnessing wind energy is an indirect way of harnessing the solar energy. So the option number 2 is also true. Question number 3. The horizontal axis wind turbines capture energy throughout the process of rotation of the turbine.
This is also true.
Yeah, because it will capture the energy throughout the process of rotation of the turbine. Fourth one,
Yes.
the band gap of a single material photocatalyst being greater than the potential window corresponding to the electrolysis of water is a sufficient condition for it to be used for the electrolysis of water. Now, just take 2 minutes to answer this. Read carefully and try to answer. Try to figure out all the conditions. What are the conditions required? And then answer. Try to just read question carefully. Because it is mentioned is a sufficient condition means can only this condition is sufficient or do we need require other conditions also? So think in that perspective. Okay. If it is mentioned that a sufficient condition means only this condition is required. There is no other condition required. Okay. So think from that perspective and then answer.
That's a false. At least minimum radiation is required. No? Only is not band gap will not help. Main at least radiation is required. Photon is required. At least.
Yeah, you
Sufficient
also
condition.
required the energy. Yeah. You also required the energy.
Yes.
Okay. And the position of band gap also required because we have
Yes.
seen the references. Okay. So the reference for the potential for the water splitting and for the reference for the band gap values, they should be in line. Okay. The valence band and the conduction band should be in line with the potential of the reactions. Okay.
Yes.
If the potential is more, it's not only the sufficient condition that the electrolysis will happen. Okay. Because the conduction and valence band should be such that the 1.23 volt is coming in between both. Then only the electrocatalysis will happen. Let me just show you that slides. So that will be more. Yeah. You can see in this slide. So this is a different reference and these data are having different reference. Okay. So suppose this is having absolute reference values and here you can say the zero value, 0 electrovolt value, vacuum at vacuum conditions, and these are for different material semiconductor. So you can see that 3.2, 3. But the location you can see this is having 3.0, but you can see the conduction band and valence band with position are different. Okay. This was 3.2. This is 3.0, but the position are different. Okay, maybe some material is having value of 2.6 or some other value, but the location is like this. Then that is not required. That will not take part in the photochemical. Okay, because it is having Eg is more than 3 or 2, but it is not in line with these band gaps required for the values required for the reaction. Okay, so we need to see the photons, we need to see this, we can come to the conclusion of photochemical reactions. So it is false. Now question number 5. Photoelectrochemical reactions involves the flow of electron in external circuit. Is it true or false? So when we are doing the photoelectrochemical reactions, then the flow of electrons is external circuit is there. So it's true. Okay. So these are the questions for today, but still we are having 10 minutes left. So let me revisit the questions, and if you are having any doubt regarding the questions, let me know. The first question was like just basic questions like photoelectrochemical reactions of water in the presence of titanium oxide photocatalysts. Space gases are generated at anode and cathode respectively. So we have to tell that at which electrode which gas is generated. So we know that at anode side O2 is generated and the cathode side H2 is generated. So the correct answer is O2 and H2. The second question is match the following steps to reach the final photoelectrochemical reactions of H2 gas generation. So we are having 4 steps and we are having 4 processes. So we have to match those steps with the process. So first of all, we know that there should be an incoming photoradiation. When the incoming photoradiation is there, that will strike on the material, and that will, if the incoming photoradiation is more than the band gap values, the Eg value is more than the H nu value is more than the Eg value, then the electron hole pair generation will happen, and then the migration of electron hole pair towards the surface will happen, and the surface there will be reactions. Okay, so the correct option will be A3, B2, C1, and D5. So A3 means step 1 is incoming photoradiation, step 2 is electron hole pair generation, step 3 is migration of electron hole pair towards the surface, and step 4 is reaction occurs. Then the use of a co-catalyst in the process of hydrogen and oxygen gas generation helps in increasing the rate of electron hole recombination. So it is false, because whenever we are using a co-catalyst, it will increase the reaction rate, it will decrease the it will decrease the electron hole recombination. Okay, so this statement is false statement. Correct answer is false. So the question number 4 is sacrificial agent added to increase the electron hole pair recombination reaction. Again, whenever we are using the sacrificial agent, it is used to reduce the reverse reaction rate and to reduce the electron hole pair recombination. So again, this statement is false. Correct answer is false. So the question number 5 is particle size reduction space, the chances of space. So we need to tell what the particle size reduction is doing. So basically the particle size reduction decrease the chances of encountering a defect in root surface. So basically it will decrease the electron hole recombination. So the correct answer will be option C, decrease and encountering a defect in root surface. The question number 6 is there are two types of windmills, vertical and horizontal. We have to tell the advantage and disadvantages. Okay. So the correct answer is A3. So the vertical axis is more turbulent flow of air near the ground. Okay. And for horizontal axis turbines, easy to access stronger winds. For the vertical turbines, wind energy is not captured throughout the rotation. And for the horizontal turbine, the complexity with respect to setting up. Question number 7 is a large wind turbine of 2 to 3 megawatt with 35% capacity factor is installed in the region. The number of wind turbines required for fulfilling the energy consumption of 500 exajoules will be. So first of all, you have to find out the energy in joules from one turbine. Okay. So in question, try to read carefully that you have mentioned 2 to 3 megawatt. Okay. So either it can be 2 or it can be 3. So first find out the energy value from 2 megawatt, then find out the energy value from 3 megawatt. So when you find out the energy value from 2 megawatt, you have given the capacity factor. So multiply that capacity factor. Also, you have given the value in watt. So first convert the mega in the simple. So 10⁻⁶ is for mega, and then for convert the watt unit is joule per second. So we need the energy in joules only. So convert the joule per second to joule. So multiply with 3600 into 24 into 365, because 1 year is 365 days. 1 day is 24 hours. 1 hour 3600 seconds. So we will get energy in joules. So it will be around 2.2 into 10⁻13 joules. So now you have the energy from the wind turbine. If one wind turbine is running the whole year with 35% capacity factor, then you will get 2.2 into 10⁻13 joule of energy. But we require 500 exajoules energy, then we need to find out the number of wind turbines. So just divide that. So just divide the 2.2 into 10⁻13, okay, in the 500 and 10⁻18. So you will find out the number. So when we divide, we will get 22. Okay. And then if suppose the power is 3 megawatt, just change the factor 2 with the 3. The 2 megawatt with the 3 megawatt. So you will get the answer will be 15 millions. 15 millions. So the correct answer is 22 and 15. So this is the formula. Similarly, based on that question only, we have to tell the space required. Okay. So basically, one wind turbine of 2 to 3 megawatt requires 0.5 square kilometer. So based on that, you can find out the space. Check all the options. Only one option is correct, because only 11 million is correct. Okay. So because we require 22 million wind turbine, so multiply with 0.5. So 11 million square kilometer will be required space for the installation of 11 million wind turbines. So these are the points and these are the process. So we already considered. A will be no power generated. B will be power available in windmill. C will be reach the rated power, and D will be windmill shutdown. So Bernoulli equation is half rho V square rho GH plus P equals to constant. These are the quiz. So first one is true during photocatalysis. To split water, hydrogen and oxygen form in the same chamber. Yeah, it's true. Harnessing the wind energy is an indirect way of harnessing solar energy. It's also true. Horizontal axis wind turbines capture energy throughout the process of rotation of the turbine. It's also true. The band gap of a single material photocatalyst being greater than the potential window corresponding to the electrolysis of water is a sufficient condition for it to be used for the electrolysis of water. It's false. And the photoelectrochemical reaction involves the flow of electrons in an external circuit is true. Okay, I think that's enough for today's class. So this video recording and the slides will be provided to you by the NPTEL team member. So those who are not able to join today, they can see the slides and they can see they can watch the video on my YouTube channel. The link will be shared with you shortly. Okay. Okay, then I hope you enjoy the session and maybe then and try to join on next Monday also. So every Monday we are having this live session 6 to 8 p.m. So next Monday we will cover the week number 8. Okay then. Thank you everyone for joining today.
Thank you, sir.
Thank you. It's a very good
Okay.
session. Thank you.
Yeah, thank you very much.